Yeah, thanks again for joining for this Voyager training. In this one, we will talk at a very high level about the architecture of the machine. And then major part of this will be how the user environment is. This is a Kubernetes-based environment. Majority of the talk will be done by Mahidar. I will just first few slides to introduce the project. But the focus, in addition to high-level architecture of the Voyager machine, which is made up of AI-focused hardware. So that's a very key component here. It is not a general purpose machine. It is for deep learning pipelines that are doing AI work. And at this point, implementation TensorFlow or PyTorch is what is the best way to use the machine. Custom codes can also work, but we're going to go there a little later in the project. Initially, it's a PyTorch and TensorFlow implementation for deep learning. That is the ideal applications. And so today we will talk about the Gaudi architecture a little bit, Gaia architecture a little bit, and the network connection and the file system. So you get overall idea of the machine, and then mostly the user environment, which is a Kubernetes based, as I mentioned, because many of you might be used to a batch scheduler, which is Slurm or PBS and things like that. It's not a big deal, almost a mirror image of, of a Slurm based scheduler to a Kubernetes based scheduler, but it does have a little bit of few little things that Mahidar will explain in detail. Is dedicated harassment-free experience for everyone, and we expect participants will follow that code of conduct. Okay, so I will jump into the project. So Voyager is a NSF Category 2 award to UCSD. I'll briefly mention what Category 2 award means. So let me first tell you what Category 1 award means. Category 1 award are for supercomputers that are available in many of the centers, SDSC, Texas, Indiana, Purdue, NCSA, Pittsburgh, which are kind of a workhorse, very stable with, kind of off-the-shelf hardware, which is ready to go with a pretty stable software stack and, provide hundreds of applications. And in most cases, in pretty much all cases, they are general purpose machines. They will have GPUs and, CPUs from Intel and NVIDIA. AMD and all of those, and pretty large machines, therefore doing science from day one. So that's Category 1 award. NSF realized that, we need to, our community jointly with you, need to keep up with future technologies. So they created the Category 2 award, where people can propose a little bit of innovative architecture. So there is some innovation. So that means, new things are being tested, implemented as a part of the project, and not a off-the-shelf thing that's ready to go and stable and nothing is changing. So under that category, we propose this Habana company, which is Intel Accord company now, who makes these Habana processors. So they make these Gaudi processors, which are specifically for training. It will only do deep learning training. It's not a general purpose machine. And we have a Gaia processor also from Habana, which will specialize for inference. So that was our innovative proposal, and NSF accepted it. So that's the thing. Category 2 is for innovative architecture. So you will see, as you start using the machine or get interested in the machine, we will have new models that are being optimized by the Habana team. Those are made available, new ways of using the machine, data parallel, going to model parallel. All of these are happening. And so we will explore those jointly with you. And again, it's for deep learning algorithms using TensorFlow and PyTorch is first we're going after. So this list all the people from UCSD and SDSC that are involved in the projects. I'm the PI and the multiple co-PIs, and HPC system support group, networking, education outreach, and Mahidar, who is the main speaker today, is the director of user services group, and Nicole, Paul, many of the people are here in the audience. So as I mentioned, Voyager is fundamentally different architecture than most of NSF supported system. It's a Category 2 award. Just to give a little history, the first category 2 award was made to Stony Brook. It was an ARM-based processor, so that was their innovation. And then the second round, 2 awards were made. One was to us, the Habana processors with Voyager, and then Pittsburgh Supercomputer has this Neocortex machine, which is based on Cerebrus, which is large-scale AI-focused hardware. Also, 2 more machines under category 2 are upcoming. One was also, to UCSD, which will have GPUs and FPGAs and distributed computing. Another one, Texas A&M, which will also, I believe, have GPUs and FPGAs. So going back to Voyager, it's a system to facilitate exploring a new architecture, in this case, AI-focused architecture in support of AI and science and engineering. That's the whole goal with this project. It's a 5-year-long project funded by NSF. And it's a departure from traditional supercomputers in many sense. And given its innovative architecture, there is a 3-way collaboration all throughout the 5 years, and especially the first 3 years is very important. The 3-way, of course, one of them is you, the AI researcher from various domain sciences who were interested in using the Voyager. That's the most important group. And the second group is SDSC experts. We want to explore jointly with you, help you provide user support, training, outreach. And third, and also very important, is the Habana experts who know the machine very well. They know the architecture, they know the software, they know which future software releases are coming, new models are being optimized for the Gaudi and Goa architecture. So this 3-way collaboration is what we want to do, especially for the first few of the project, to help your application, explore the machine as optimally as possible. And so there is a learning curve for all of us. Although in our experience, and Mahidar may talk about some of these, porting initially, some of the code did not require to change anything other than pointing to the Habana processing unit instead of a GPU, just few lines or a few words in your code or how things are run. So the way we propose the Voyager machine, and most category 2 machines are proposed this way also, is the first 3 years is we call test bed phase. And the last 2 years is the allocations phase. Allocations phase is how all the category 1 supercomputers are allocated. Like any researcher who wants to use a category 1 machine will write allocation proposal. It will be peer reviewed, and based on the review, the researcher will get time, all of it, or maybe some of it if the reviewers think, they didn't justify everything they requested. So that's what will happen to the last 2 years of the Voyager project. But the first 3 years is the test bed phase where, given its innovative architecture, we want to work with select group of users over a period of few months, jointly with SDSC experts and as needed help with Habana experts to port, optimize, scale, and explore various architectural feature of the Voyager machine jointly with you, the research group. So the first 3 years, we are kind of deciding which are the appropriate applications, and then picking, given, the machine is not huge, it's a moderate size machine. And however many users we can have deep engagement with, given how many, support we have within SDS, although NSF is funding us to do this kind of work, it's not unlimited, funding. And we want to make deep engagement with some users group. So we will, say we talk to many of you, then identify which, maybe all of you are appropriate for Voyager, but since we have limited size of the machine and the number of people on our side, we may pick few user, 5-6 group, we onboard them in the first few months. Then as they are going, maybe some of you will find it very interesting, some of you not so interesting. Then the next few months we onboard another group of users. So that's the plan of managing the onboarding of users. Okay, so as I already mentioned, there are specialist training processors called Gaudi, special inference processor Goya. That's the key feature. Deep learning models are used here. And again, PyTorch and TensorFlow implementations is what we are looking for. And then we want to engage with the community, explore their large models, and see what does it mean for the AI community to have an AI-focused hardware instead of general purpose, like GPUs, right, which will do AI as well as other scientific computing, but just to focus on AI-focused hardware, which is specifically do what does it mean for the AI science community. That's what we want to explore with you. We want to do, engage the broader science and engineering community and have industrial engagement and do a lot of training workshops and white paper So again, I already said this, the first 3 is the test-based phase, followed by your allocation phase. In the test-based phase, we will, as I said, explore the innovative architecture. We will have workshops and user forums, and the lessons learned. We want to learn from you as you use the Voyager, and then share that lesson with the community so that the whole community gets an idea of what it means to have AI-focused hardware. And we have external advisory board. We will guide us on many of these projects. And during the first 3 years, we will also figure out what does it mean to allocate a machine like that. Do we allocate in Goa training node hours? Do we allocate in Goa inference node hours? Do we allocate on both? What does it mean for AI-focused hardware to be allocated? And many of the things in the allocation phase will be same as what in the test bed phase. Again, workshops and user support, sharing information with the community. Onboarding process for research teams to Voyager. I already mentioned this, given that we have the moderate size of the machine and how much deep engagement we can do with how many user group, we will talk to all of you who are interested. Make sure your model in TensorFlow or PyTorch or even deeper down the model is appropriate. It's already, similar models are running on Gaudi and Goa architecture. And then identify few groups in the first few months and another group the following few months. And that's how we want to manage the onboarding and working, having deep engagement on one-on-one. So I will hand over to Mahidar. I just wanted to list many of the people here. I'm sure there are other people who have contributed to bring the machine to current test bed phase. And especially we want to thank our data center and HPC systems people. As you know, in the last, although we are in a coming out of COVID very well now, I hope. And but during the last year and a half, many of these people had to come into SDSC and work under challenging condition to bring the machine to where we are today. I will hand over to Mahidar, and anytime you have a question, you can either post it on the chat or I will wait for a few minutes if you, as Mahi sets up, if you have any questions for me. Mahidar, I think you can start.
Thanks, Amit. So the slides look okay, right?
Yes.
Thanks. Thanks, Amit. So I'll start off by just giving a high-level overview of the system hardware, and then kind of go into in-depth kind of architecture for each of the nodes, and then briefly kind of look at how the software stack is laid out, and one quick example of like the kinds of changes we had to make to port one of the deep learning models to the Gaudis. So we have 42 Intel Habana Gaudi training nodes, and each of these training nodes has eight of the Gaudi processors. So we have a total of 336. And there's all-to-all networking between the processors on a node, and I'll go into the network architecture a little bit more in detail further down the talk. And then the Gaudi processors basically they feature specialized hardware units for AI, and they have HBM2 memory and on-chip high-speed Ethernet. So again, details coming in the coming slides. And we have 2 Goya inference nodes, each with 8 Goya processors, so 16 total. In addition to these deep learning specific nodes, training and inference nodes, we have 36 regular compute nodes with Intel x86 processors. This is for basically general purpose computing, if you have any prep data processing that you have to do and so on. And it also, these nodes can be used for launching the multi-node Gaudi training jobs, basically. So, and I'll give an example of this in the second talk, like on how to do those things. The primary network between all the training cards is a 400 gigabit interconnect using RDMA over converged Ethernet. So it's a pretty standard technology in terms of the network, which makes it easier to deal with and set up and use. In terms of storage, we have 3 petabytes of storage, and again, this is connected via a 25 gigabit connection to each node, and this is deployed at Ceph right now, but as Amit mentioned, this is as an experimental kind of system right now, and we're in the testbed phase. So we're going to be open to reconfiguring some of the storage to be deployed in other ways. And we have a 300 plus terabyte home file system now, which is also available on all the nodes. Oops. So let me go to the training nodes. So this is a little bit more detail on the training nodes. So this is super micro integrated Gaudi nodes. There are 8 Gaudi HL205 mezzanine cards and 32 gigabytes of high bandwidth memory on each of these cards. And the host CPU is basically a dual socket Xeon 3rd generation processor with 48 cores on each of the sockets, basically. And then you have 512 gigabytes of RAM on each node and 6.4 terabytes of NVMe drive. And this you can use as scratch space when you're doing your training. And each node has basically 6 400 gig scale out connections. And again, I'll go into the networks detail a little bit later, but so you can see it's quite a bit of, 2.4 terabits of network connectivity going out of each node. So it's quite heavy on the network side. And then 2 25 gig Ethernet connections into each node. So that gives you the 50 gigabit. That's for all the storage that's coming in. So the processor itself, the Gaudi processor is architected for performance and efficiency. It's kind of, it's specialized for training, as I mentioned. So there are fully programmable tensor processing cores, and there's a whole tool chain associated with them. And then there's a configurable matrix math engine, basically a gem component. And then there's a multi-stage memory hierarchy, but the main thing to keep in mind is you have 32 gigabytes of HBM2 on each of the cards. And then the last bit there is the unique part. It's got 10 100 gigabit Ethernet on-chip connection. So this is what's used for scaling out when you're using multiple cards and multiple nodes. So that's the thing on chip there. On the inference nodes, as I mentioned, we have 8 of these Goya inference cards on each node. Each of the Goya cards has 16 gigabytes of memory, and it's DDR4 memory. Again, this is a dual socket 2nd generation processor, Intel processor. And then you have 384 gig of RAM on each of the nodes. On the inference node, we have 3.2 terabytes of local storage and the same 50 gigabit Ethernet going into the nodes. And again, the Goya architecture is also very custom for inference. It's got 8 tensor processing cores, has the same kind of configurable matrix map engine, 16 gigs of DDR4 memory, but no HBM2 on this one. And there's a little bit, the shared memory here refers to the on-chip memory, which is a little bit larger in this case. Then the compute nodes for general purpose computing, and also you could use it for inference in some cases. So you have 26 cores per socket, so 52 cores per node, 384 gigs of RAM on those nodes. Again, 3.2 terabytes of NVMe for local scratch storage, and the 50 gig Ethernet going in. So as you might have noticed from all the different nodes, there are different distinct networks. So the Voyager has 3 different networks that support basically application performance, data movement, and then systems management. So there's the 400 gigabit network, which is essentially for scale out of the training aspect. So the way it works is you have 6 of these connections from each Gaudi node to a single Arista switch, non-blocking switch. And then 25 gigabit bonded control and data network. So each node has 2 of these. So you have a bonded 50 gigabit link going into each node. And then out of band, there is a 1 gigabit network for managing the nodes and IPMI access and so on. Which for the end user, you're not going to see this part of it. You're just seeing the first 2 parts. This part is more for the systems team to be able to manage and do remote console and those sort of things. So I mentioned the specific network aspect of it. So now I'll go into a little bit more detail. So as I mentioned, 8 Gaudi cards in each node. So the way it works is, so now if you remember, I mentioned each of these Gaudi cards has 10 100 gig connections, right? So the way the network is laid out, you do an all-to-all to all the other cards on the node, right? So it's all-to-all direct routing. So every card has 7 connections basically going to the other 7 cards on the node. So that leaves you 3 network cards. 300 gig connections per chip, right? Those are aggregated into 6 400 gig connections going out of the node. So because it's 8 times 3 gives you 24, that's the 24 here, 24 times 100 gigabit. And that's basically bundled into 6 400 gig connections going out of the node. So you can see within a node, you have basically full all-to-all connectivity with basically direct connection. So there's no blocking aspect there. And then externally, you have 2.4 terabits going out of each node, which is not bad. From a scale out perspective, it's pretty good. So this is pretty much the same kind of information, but just showing you a system block diagram. So you have the CPUs and the PCI switches. So you have 4 cards on each of the PCI switches. And as I mentioned, there's all-to-all connectivity, and then there's the basically each OEM connects to the QSFP connector with 300 gig per second, because you have 3 connections left over, and then that's basically switched into a 6 400 gig connections going out. So what this does is lets you scale out to really efficiently scale out to really large counts. And we've tested up to 128 Gaudis with very good performance, and we are right now doing some tests for the full kind of 256 card performance. And we expect that it should do well with this kind of networking setup. So, and as I mentioned before, it's natively integrated Rocky on each Gaudi processor, so RDMA over converged Ethernet. So we basically use a regular 400 gig switch from Arista for this. There's no proprietary network or custom thing to do in this case. So overall, that means it's 42 nodes, right? Times 6 times 400. So you're talking over 200 terabits of bandwidth in aggregate going out to the full system. So that's So basically, if you have all these nodes going into the big Arista switch, which is completely non-blocking, 230 terabits per second switch. So that's the training network aspect of the system. But there's also another network for data and control. So every node has 2 of these 25 gig connections. And the Ceph OSD nodes, which is basically the server nodes for the storage, have also another 550 gigabit bond for their backend network. And this is set up in a redundant way. You get about 200 gigabits per second aggregate link between each pair. So you could lose a switch and still have connectivity, essentially, from a data standpoint. So so we have a storage hierarchy essentially on Voyager to support the AI workflows. So there is node local non-volatile memory, which is made available as an XFS file system. As I mentioned, 3.2 terabytes on the compute and inference nodes and 6.4 terabytes on the training node. So you have a fair bit of NVMe on each node that you can use for your training data sets. And in my second talk, I'll talk about how this is made available within Kubernetes. But so that's one aspect of it. Then we have the NFS file system for the home directories. That's 300 gig. You can basically put your code and models and so on in there, and that's another location. And then the project storage, right now, as I mentioned, we are using Ceph, but we're going to experiment with different file systems there. So that's kind of the hardware side of the system. In terms of science applications, this is just a table that kind of shows the kinds of AI techniques people have used. And these are all kind of projects that we took on during the early user period. So we kind of have ported some of these to Voyager, and so just wanted to give you a flavor of the kinds of AI techniques, like and the keys on the side on the right here. So you have the dense neural network, variational autoencoders, GNNs. So quite a few standard techniques that you all might be interested in, and quite a broad range of application domains. So you have like astronomy, atmospheric sciences, biochemistry, chemistry, data-driven weather, genomics, high energy physics, and the image analysis and system biology. So quite a bit of range there in terms of the scientific applications that have been running on Voyager. So in terms of the porting itself, the porting has been relatively straightforward. Like several applications are running on the Gaudi, a little bit on the Goya on the inference side. And then so far, our experience is the codes don't need major changes. What we typically do when a new group comes online is to kind of have a quick discussion. As Amit said, it's usually a 3-way between SDSC, the researchers, and the Habana experts. And we take a look at the models that the code is using, and the operators that the code is using, and see what's supported and what's not supported, what's on the roadmap, and so on. And typically, we've found that most of it is okay and supported. So we can, once we have that, we look at the code changes that are needed to kind of move people on. And it's not been a major change so far. And we've always got strong support from Habana on this aspect. So that's been really nice in terms of getting very directed help when we are onboarding users. And we have done a lot of training based on our experiences so far. And we do have Jupyter notebooks possible on the Gaudi. I'll kind of give you the process in the second talk. It's a little complicated right now. We are hoping to simplify that, but it is possible to use notebooks if that's what you're comfortable with. But as Amit mentioned, the key is that right now we are working with TensorFlow and PyTorch frameworks for the most part. Now the software stack itself, as we mentioned, at the highest level, you have PyTorch and TensorFlow frameworks being supported, and there's a bridge for each of them that goes into the underlying Synapse AI stack that makes things available. So there is a C API if you are really brave and want to write your own code, but we haven't got into this aspect yet, but there is a API available if you really want to do that. So there are Habana kernel libraries, there are Habana communication libraries, and there's a graph compiler that sits under the bridge level, and there are the drivers, and then at the embedded software level, you have the system management, firmware, and so on. So that's the kind of the stack overview. The one thing that is different, at least for traditional HPC users, we are not used to running this way, but is that the stack is completely containerized. So all of this sits in a Docker image, and Habana is regularly updating them with the new versions of Synapse AI. And we can also layer on top of this and build our own custom Docker images if it's needed. So, and these Docker images are available on the publicly available on Habana's Vault. And so you can grab that as a starting point and add the packages you need. So for example, you might say, oh, I need these extra Python packages on top of what's in the container. You could go ahead and do that and build another container that you can use. So a quick porting example, this was a code out of UCI that uses Keras to implement the model, and Habana has TensorFlow Keras. So it was really very lightweight in terms of change. So instead of using import Keras, we just translated it into the TensorFlow Keras version. Took a function call to load the Habana module at the beginning of the execution. So, basically that initializes all the things you need for the Gaudi. And in this case, since the code was set up with the APIs based on the external Keras, we had to just replace that with the corresponding TensorFlow Keras API calls, which wasn't a big change in this case. Code. And once we did that, and they had a custom loss function, so we had to disable the eager mode in this case. But with these changes, the code ran pretty well on the system. Then I want to just look at an example which is using Habana Horoward. Again, this is built off the standard Horoward setup. So if your code already uses Horoward for scaling out, you can pretty much replace things with a Habana version, and that should work as is actually. So if you look at the changes for the distributed training, it's pretty standard, right? So we are still loading the Habana module and then just importing Horoward, doing the Horoward init, which is the same thing you would do on like a GPU, for example, if you're using Horoward, that is. Download the data set and use the Horoward optimizer. So as you can see, for the end user, this doesn't look very different from what you would do on a GPU, right? I mean, there's minor additions and then things go on. So yeah, so the early user experience has been through TensorFlow and PyTorch frameworks. and we've basically helped users with either the Habana provided Docker images or layering in packages on top of that. And the jobs are run using Kubernetes and Voyager, and this will be the discussion I'll have in the second talk. And I'll also do a demo so you can see how to launch the jobs. And I see something in the chat. There was a question on, well, is there a way to check for presence of Habana? Right now, we are kind of doing this more with a feature in Kubernetes. You'll see that you'll request the feature, so you will know you are going to be on a Gaudi node if you request a Gaudi. So it's unlikely you'll land up on a compute node and look for a Gaudi, basically, because of the way Kubernetes is being used to set things up. There was a question of, can you pull a Docker? Yeah, you can pull them from, I think, anywhere. We have users who have modified things and put it on Docker Hub. We've had users modify things and put them on GitHub. It's all fine. You can pull from I mean, there's network connectivity to the external world, so you can pull basically. But the key is you need to start with the baseline Habana container, because that has the Synapse AI stack and all the TensorFlow and PyTorch versions that are set up to use the Habana hardware. So that's one thing to keep in mind when you're installing things. Make sure you don't install the base TensorFlow and PyTorch from somewhere else, because then that's not going to recognize the Habana hardware. But other than that, yeah, the containers can be external. Eventually, we are also thinking of doing a GitLab instance within SDSC, but that's not set up yet for external users. So going back to the summary, so there's multi-node training options in both TensorFlow and PyTorch. TensorFlow, you can use Horvath, or you can use HPU strategy, which is kind of a TF-dist equivalent. And then PyTorch using torch distributed and kind of HCCL for the backend. And some of these details will be there in the second training that Habana experts will be at, and in November. So you like if you have like deeper questions about how these things are done, that will be in the second training that we do. There are profiling options in both TensorFlow and PyTorch. Again, this will probably get discussed in the second training. And there's Voyager documentation for some info. And I have links at the end of my second talk with all these locations, like the Habana developer site and GitHub, with lots of reference models, kernel libraries, and so on. So I think I'm over a little already, so I'll stop here. Let's see if I had anything else. Yeah, I think this is just a summary that Amit already kind of mentioned, the partnership and so on. One thing is, if you are interested in gaining access, email us at consult@sdsc.edu. Please do it at a group level. So because what we typically do is, once a group requests access, we set up a call and kind of go over the models and see if it's appropriate, or if it's already supported, we kind of get you on. If we know that, hey, that's coming down in the pipeline from Habana a little bit later down the road, we might hold off and say, hey, like when things become available, we'll get you on. But we can start with an email and then we can follow up with the call, basically. So I'll stop at this point, and if any more questions, go ahead. Thanks. All right. So the second talk basically is just an intro to using Kubernetes on Voyager. So let me get going. So this is just there for completeness in case people look at this talk in isolation, but we just went over all of this, so I can skip this part. So just a quick outline. We start with a Kubernetes overview. just all the components and the objects you can work with, and concept of namespaces. Look at the kubectl command and what you can do. And we'll do some examples, basically a simple TensorFlow case, file system access, multi-node kind of example. So in terms of accessing Voyager itself, we actually do have a login node, even though with Kubernetes, we don't technically need one, but we have one. So Voyager has a login node, login.voyager.stsd.edu. So you just SSH into it. You can use basically on Linux and Mac, we just use the terminal, and there'll be an installed SSH application that you can use to connect. On Windows, you can use a terminal app or install something like Putty or Sylvan to access Voyager. Now, just a kind of brief overview of Kubernetes in terms of components. So there are two planes. There's a control plane, which is basically where all the global cluster decisions are done, like the API server, the kube scheduler, the controller and manager for Kubernetes, and then storage for Kubernetes specific stuff. And then there is the node plane, where basically you're maintaining the running pods and provide the Kubernetes runtime environment using kubelets and kubeproxy. The main thing from an end user perspective to remember is that you're not logging into the node directly, or you're not running jobs on the node natively. You're running them through pods. And in the pod, you'll have the container, which has the right environment for whatever software that you're trying to run. So Kubernetes objects are basically persistent entities in this system. So the object can basically describe the containerized application you want to run, that the stack is in the container, as I mentioned. It can describe the resources needed by that application, like the CPUs, the number of Gaudis, memory, so on. You can also set policies on how this application behaves. And then this kubectl object can be used to essentially create this object based on whatever resource requirements and this environment that you're requesting, and then run things within that. So the object configuration, you can describe using JSON or YAML files. We are basically doing YAML files for our case. There's more detailed Kubernetes documentation if you want to go deeper into this, but that's kind of the quick overview of how things are. Now, in terms of objects, the smallest deployable unit is a pod. That will include resources, containers, storage, and run policies. You can have a job that creates one or more pods. For example, if you have an MPI job, which is a kind MPI job, it will create a launcher pod and then worker pods where the actual MPI tasks run. So a job can create more than one. There are a lot of other options because Kubernetes, is widely used for deployments and kind of services and so on that really don't apply to the way we are running on Voyager. But you have deployments, you have replica sets and cron jobs and controllers, and all this kind of provides redundancy and moves jobs around if something fails and so on. Not so relevant on Voyager, but you could do some of these things if you want to. And it could turn out that one of you has an application that needs something that's more of a service. But right now, we just focus on the first two, like the pods and the jobs. So everything is managed using kubectl commands. When you log into Voyager, we load the Kubernetes module by default. So you will have kubectl in your basically default path. So since the pods and jobs are essentially the equivalent of our Slurm jobs that we are used to on an HPC, so you have similar things to list the pods that are currently in existence. So you can do get pods and list pods in a current namespace, default namespace. You can make this a wide listing, which means it will give you a detailed listing. If you have a YAML file, you can basically create a resource. I mean, basically the equivalent of submitting a job, but in this case, it creates this object, right? So using kubectl apply. And when a pod is running or completed, if it's if the pod is currently listed, you can get the logs for the pod. And this is where all the output's going, basically. All the standard output is going into these logs, in addition to other things if there are errors and so on. So you can do kubectl logs and the name of your pod, and that will give you the logs for the particular thing. And I'll do a demo showing all of these kind of commands. And once you're done, one thing you have to remember is this object is kind of persistent, so you need to delete it if you're done, like explicitly. And there's a nice cheat sheet reference I have with more commands if you're interested. So let's start with a very simple example YAML file for the Gaudis on Voyager. So we are basically saying the kind is a pod, so it's a single object there with a pod, and then we give it a name. So HPU test pod. One thing to remember is that this name needs to be unique. You can't like have multiple pods with the same name. So that's one thing to keep in mind. And in the specs, you can basically give the containers info. So like here, the image that I'm pulling is from Vault. And this 1.6.1 is the current Habana Synapse AI version. And I'm pulling an Ubuntu container with TensorFlow 291. And just pulling the latest version of that container. And there is the equivalent of NVIDIA SMI, which is HLSMI, which basically gives you information about the hardware, basically, the Gaudi hardware, and what's running on it and so on. So it looks very, it'll be very familiar to you, the output. And then in the pod, you have to say what are the resources you need, right? So you can request, like we're saying, limit of 4 CPUs, 16 gigabytes of memory, huge pages, and this is needed for getting the training to work there. And then the key is we are doing habana.ai/Gaudi:1, which is saying, give me 1 Gaudi card. So let me see if I should basically run this so that, so I will share the entire desktop. That might be better.
There was a quick question on the chat.
Oh, okay. Did I miss something? Hold on. Let's see. Do we always have to use the container images, or can? No, it has to be the container because the Synapse AI is in the container, and also even on the compute nodes, Kubernetes is expecting a container when you launch the pod. So that sets your environment. But within that container, you're running basically Python normally, right? There's nothing. And I'll show you an example, basically. Think of, so if you log into one of these compute nodes, and I can, Gaudi nodes, I can show you there's nothing installed, like other than the drivers. So if you can't do this, but I can, let me, oh, I'm not sharing it. Can everyone see my desktop?
Yes.
Okay. So I'm just going to do this, and you This is going to be a little slow, I think. So you can see all the nodes, and if I go to one of these nodes, there's basically nothing installed there other than the drivers and the configuration. So, right. So if I say go to /opt, there's very little there, like, right? And so all the environment comes from your container. So everything that you set up will come from the container. So let me show the simple case now. So I have this YAML file. I'm basically running just getting one card and running HLSMI in this case. And this is being done in the standard container I'm pulling from. So if I do kubectl apply -f that, so it says the pod got created. And now if I do get pods, you can see it's already completed because it's a pretty quick thing. And if I do logs on that, I can get the output. So you can see the HLSMI output. So we have one HL205 card because I asked for one card, and 32 gigs of memory on that card, if you remember. So it's like, the output is that we didn't run anything on the nodes on the thing. So there's nothing, no process on the card itself. So, but that was a quick, simple example of running a command using the container environment. Notice it pulled the container, it got the container running very quick. It's because I've been using this container for other things. So it's already cached on the nodes, and it comes through very quick. Looks like there's another question. That's a question I'll have to go check on kubectl free, unless someone on the call has the answer already. But that reminds me, I didn't actually.
There's another Sarthak Bhatia has raised hand. I think wants to ask a question. Please go ahead.
Oh yeah, go ahead. Yeah.
Yeah, thanks for the presentations and demos. The reason why I was asking about container images and Metal Python code is because there would be at least in the beginning, I would imagine a lot of prototyping required for the code, right? So, doing it via containers might not, it would generally be very time consuming, because we would need to create containers every time.
Not necessarily, because what you could do is actually you can interactively access this, right? So what you could do is actually get the baseline container, and you can mess around with packages that you want to install in Python, and that's all fine, right? You can interactively do that.
Yeah, I was not talking about Python Python packages installation specifically. I was talking about more on the side of the source code.
Yeah, even that you should be able to change, right? That's not a problem. I should make it clear. You don't need to stick your source code into the container. You can always have it on your home directory and pull it in.
Got it. Thanks.
Yeah. So I'll show you one example actually where I'm doing an interactive session, and I think I do have a file system pulled in there, and you can look at it that way. So yeah, you don't have to do. You can pull in any file system that's mounted on the host into your container. You can bind it in basically. So
that's what I was going to ask. What level of access would the containers have to the file system? But yeah, if you're saying that we can do installations, then I guess it's both read and write.
Yeah, it's both read and write. The container runs as your UID and GID. It's a little tricky because it won't, like when I show you the interactive one, you'll see it doesn't know your username in the container. I mean, because we don't have a password file in the container, but it will know, it will run, Kubernetes will run it as your UID and GID. So as long as you keep that consistent, you can read write fine into the file system.
Okay, thank you.
So let me, yeah, so let me go on, and then I'll actually have to delete that container that I have there. So I'll do that later. Delete that, sorry, object that I have there. So the Kubernetes namespaces, they're used to manage the cluster resources between groups. So on Voyager, we kind of have two default ones right now. Like there's a restricted user specific one. So you will see $user-restricted. So for example, in my case, it'll be Mahidar-restricted. So when if you just do a kubectl apply with no namespace specified, it will put you in this namespace. I mean, it'll launch everything in this namespace. You can specify the namespace either in your YAML file, or you can do it at apply time. Like you can just say kubectl apply -f your YAML and then do a -n and whatever namespace you want to launch it into. We also have a default namespace that actually runs in privileged right now, and that's needed for the MPI cases. We are trying to change this so that even that runs in the user restricted space, but at this point, MPI works only through the default space. So that's another location. And kubectl, as you saw, is basically what we use to deploy applications, like inspect and manage the resources. And what kubectl does is looks for a file config in the $home/.kube directory. So, like I mentioned, you don't really need to run this on Voyager, this kubectl command. You could have kubectl installed on your laptop, and you copy over the config file that points to Voyager from our .kube directory in your Voyager home directory. And you should be able to run that kubectl command from your laptop directly. You don't even have to go into Voyager. And then on Voyager, we do have a Kubernetes module that's loaded by default that gives you kubectl. If for some reason you unloaded the module or change something, you can always reload it using module load Kubernetes. I already showed you this. When I do kubectl get nodes -o wide, it basically tells you the entire availability of all the nodes on Voyager. So you can kind of see all the different types, different nodes. Now, we also looked at this. I just showed you the output, so I'm going to skip this part. And we saw the resource request, right? You can basically request the CPU and memory that you need. That's all done. So now we get to an example where we are doing something, right? So in this case, what I'm doing is just a very simple TensorFlow example from Habana. Their model reference GitHub site is nice. They have a lot of examples for standard models. You can take a look at that. And that can be your starting point, actually, to kind of run things. But in this case, I'm basically setting up a few things. I'm basically creating a temp directory, running HLSMI, cloning that repository, changing to that location, and running the Python example code. And you'll see output looks something like this. The HLSMI output, and then output from the TensorFlow part of it. Now comes the file system usage question. So here's a snippet of what you can do. So there are a few things that you can have in terms of file system. So one is the Scratch directory local to each node. Remember the NVMe that I was talking about, the 6.4 terabytes. So that Kubernetes has this concept of an empty dir that you can mount in, which basically is ephemeral storage. It's mounted as Scratch, and once the pod is deleted, that this directory is also gone. So think of it as local Scratch that gets purged at the end of the job. That's the equivalent, basically. But as I mentioned, you can also pull in any host path you want. So like you can say host path /home username, as long as you have permissions to it. So this is in your home directory, and you can pull this in basically and mount it wherever you want. And you can specify the mount path, and I'm basically putting it at the same location, so it's not confusing. So it's /home username. So in this case, if you do this kind of setup in the YAML file, you'll have both the home directory and the local Scratch. Now you have three options, as I mentioned. You can get home directory using host path, Ceph using host path, and node local NVMe mounted as Scratch. This is the current setup. We will likely get Ceph block storage at some point, so that or mount Ceph in a different way into the container. All stuff that we are going to test. But right now, this is how we've set up. So it's quite simple in that sense. So interactive access. So I know some of the Kubernetes admins don't like it, but the easiest way to do it is to put a sleep command in the command, and then you can just log into the thing. So let me do this example because that might. So you can still see my terminal, right?
Yes.
Okay. Let me see. So let's look at this. So basically, I am pulling in Scratch and empty and this directory, right? The home directory in this case. And actually, you can specify the working directory. And in this case, I just said I'm going to go into this working directory. So let's check what's running. So this is in my default namespace. I'm going to delete pod.
Hey, Mahi, I think I want to clarify. I think Kenneth's question was regarding kubectl delete, not free.
Oh, okay. Yeah, which is exactly what I did right now. So you can delete the pods, or you can delete everything that's associated with the YAML that you use to create the object. So you can do kubectl delete -f and the YAML file name, and it's going to delete all the things. So so that's release the thing. So now I'm going to apply this one. And if I do a git pods, you can see it's running. So once a pod is running, you can always log into this. So if you're doing some interactive kind of like the question about making source code changes and trying things out, this might be the way to do it. Just do a kubectl exec -it and the name of the pod. Oops. And let's go in there. And I'm just going to run bash. So notice how it says cannot find name for group ID 300. This is because the password file doesn't exist. But my group is use 300, which is got a group ID of 300. So it's going to create the files with the right. So you can see it landed me in the working directory that I specified. And this is in my home directory. And I can actually go into my home directory and look at things and the files are there. So so you can make changes here, run interactively, like I can do HLSMI here now, and you can see the thing. So you can try out interactive things this way. And when I'm done, I just do kubectl delete -f, and it's going to delete that pod. So hopefully that's kind of good enough for the kind of development that you are trying to do. I think that. But in addition to this, you can install packages. So we have cases where we temporarily install like some Python packages you can pip install it into a different location and then just update your Python path to it. So what we've seen some users do is kind of they do all these installs using pip into the local directory, try things out. Once they settle down on like the packages they need, they go back and put that into the container so that it's permanent and they don't have to keep doing it all the time. And then they can use the modified container for everything. So that's kind of the workflow I would suggest, is try it out with a local install and then stick it in a container and kind of make it permanent. Because the container building can take time, so that's probably not something you want to keep doing all the time. So we looked at this, basically a snapshot showing the interactive access. So the next thing I want to talk about is the kubeflow MPI operator. This essentially enables multi-node scaling, and it uses it's optimized for all reduced style workloads and uses the Habana hardware and software. Originally, they had a Habana specific MPI operator, but now it's been kind of now they've kind of modified things so that it uses the kubeflow MPI operator, which is a pretty standard Kubernetes thing. It's not something that is Habana specific. The main thing is there are some configuration files that are generated and put in, and this is the thing to remember is the MPI tasks get launched over the regular network, but actually I should probably show you that. Let me quickly go back to the terminal and SSH into the node. If you do an ifconfig-a here, you're not going to see the 400 gig interface. All these are interfaces that are more local. The 25 gig, the bonded one that you see here, you can see basically that one, but you don't see the 400 gig interfaces at all. And this is because those network cards are not on the node, they're on the chip. And that network is actually completely independent of the host network. So you have to keep that in mind. It took us a while to get used to that because we are used to seeing all the network cards on the host and kind of using them. But in this case, what happens is essentially, and this is the end user doesn't have to worry about this. This is kind of taken care of by the Habana software. Is that and the configuration is that when you get assigned these cards, this config file will have the info for the connectivity for the 400 gig network, and that's what gets picked up when the Habana software is launching the multi-node training and so on. But you don't need to worry about it. It's just something to keep in mind that you won't see the network that's being used on the host. So here's an example file which is doing the multi-node case. So now you'll see it's a little different. The kind is an MPI job. So it's a job instead. So it's going to launch multiple pods. And you still have a name. And you can notice here the namespace is set to default because that's where it runs right now. Once we kind of figure out a way to make this run in our regular namespace, we can take that out, but right now it runs it in default namespace. So you can see now there are some specs, right? So there's slots per worker. So we have 8 cards per node. So we are saying slots per worker is 8 in this case. We are basically doing a launcher pod, which if you look at it, it has the host path set. So because I'm going to launch from a home directory, it's got the scratch, the local scratch if needed. I'm using the TensorFlow 2.9.1 image again in this case with the mount pods. And I'm running this command. And if you look at this command, it has the MPI run in it. And I can show you that a bit later. And then there are worker specifications. So that pod specification was for the launcher. Then there's the worker specification that says a replica of 2. And so we are basically going to have 2 worker nodes. Saying that the service account is my service account. And then the volumes are set and as before, and the working directory is set in this case. And this is like a hello world example that I'm doing. Now, for the worker, you can see that we are asking for 8 Gaudis, 8 CPUs, 256 gig of memory, and 16 gig of huge pages, and basically doing the mounts. We're also setting this environment variable home. This is because it's not set by default in the container, and that's needed for the TensorFlow to work. So I'm just pointing the home to /scratch, but you can point it to the /home either if you want to. That's fine too. I mean, username if you want to. So once you launch this, you will see there'll be a launcher container, a pod, sorry, and the worker pods. So let's go ahead and do this. Hopefully there are enough nodes free that I can do this, but let me just do that. So I'm going to go into, let's see, what's my MPI. So if first thing I can just show you what's in this run forward. So it's basically doing an MPI run. Notice it's saying allow as root. It's because we are running privileged in this case. So be careful when you run MPI. And the Python path that I'm setting just for the model reference, that's about it. And it's running basically at the Horoward example. So let me do a kubectl apply -f dot. Okay. So if I do kubectl get pods, it says, hey, no resources found in my either restricted namespace. This is because this is sitting in the default namespace, so I can do this. And you can see it just started. And I think it should be running now. Yeah. So notice it failed once. I think it's because when I was checking this before, I noticed that if one of the workers was not up, it would fail and then come back. Now, one thing you can do is you can use the kubectl describe command, and you can basically pick one of these, and I'm going to do end default because that's where it is. And that gives you, oh, I think I need to put pods in there, sorry. So kubectl describe pod. So it actually gives you the full details of how that particular pod was launched, like, the start time, all the labels that it has, the IPs, what it is controlled by. This is controlled by the MPI job, the image ID, like when it was started with the resources, and it actually gives you kind of how it created and assigned all these things. So it's pretty nice in terms of details. And it's also useful when you're debugging problems, because if there's some error, like, so let's see how this looks for the pod that we saw errors on, so, or relaunches. So you can see that it did the usual launching stuff, but if you look at the details here, it tells you what is going on, right? It successfully pulled, where did it start? Yeah, it got the assign, but it had basically back off the restarting the failed container, right? And then it tries it again, and when things are correct, it will come up. So you can kind of see the details, and if something goes wrong, it will point it out here. So that's a good debug option, basically. So now getting back to the pod, now you can get logs for each of these. So you can look at the logs for the TensorFlow worker. Oops, it didn't find it because it's in the default. So you can see not much output there. It's just the SSH stuff, and it's the disconnect after the MPI run finishes. But if you look at the kubectl logs on the launcher, you will see that's where all the output is, basically. So you can see basically it's setting up the server. One thing is it's got some information on some optimizations that can be done. And right now, our Habana driver is a little older than the version of the container that we're using, but we've confirmed with Habana that this is okay to do in this case. Usually we have the same matching thing, which will happen the next time we update, which should be soon. Like I think the 1.7 is coming out soon. So, and then we won't have this, but then it it gives you all the info about the horovod it's using, the CPU info. This is all pretty standard stuff, and then it has the training output there. So one thing is the workers are still running, so I can actually go to the worker pod and see what's going on either also. Like, so I can do exec-it. I need dash and default, and I can look at this now. Notice I'm in as a root right now. So now you can see, since we asked for 8 pods, all the 8 pods are showing up. Sorry, 8 Gaudi cards. You're seeing all the 8 Gaudi cards. So let me go back here. So that's the multi-node example. So one thing to keep in mind, let me go back to the specification, is that all the job the MPI launching is happening on the launcher node. So you need to make sure that you mount your working directory into the launcher node as well, not just the Gaudi ones. And also, this is running as privileged. So if it creates files, it's going to create files with the wrong UID and GID. So make sure you change them to your UID and GID. And you can just have another command after this command that says, chown your UID colon GID, and then all the files that you want to change. As I said, we are looking to change this so that it doesn't need root, and like we can run it in normal each user specific restricted space. But right now, this is the right setup. And for most of you, I think starting point, I wouldn't even get to the MPI part. I mean, there's a lot of development to be done just for the setting up of the standard kind of your software porting and all that takes a little bit of time. All right, so the next example is a PyTorch example. So you can basically export home again and clone the model reference and basically doing that. So the only difference is I'm pulling the PyTorch image from the Habana vault. And in this case, it's 1.12 is the version that I'm pulling. And we looked at this described example already, so I'm going to skip that. So the next example is a Goya inference node example. This has a slightly different setup from a stack perspective. I mean, it has a different version of the stack. So there's a container that one of our consultant, Marty Candace, developed, which basically has the Goya like Synapse AI software and all the packages that are needed to kind of run on the Goya. And in this case, again, I'm basically changing to /scratch, and here I'm pulling in a file from within. There's a demo directory that I tarred up that I just extract into /scratch and then run that demo. One thing to keep in mind is the Goya framework is not right now. The software stack doesn't support the newer TensorFlow. So what you will have to do is use the Onyx approach. So export your model to the Onyx framework and then use that, and that should work fine within the Goya. And we can help you with this process if, along with Habana's help, if you're interested in going that route. So in this case, it was a simple BERT benchmark that they were running, and we were running this multiple times just so that it was long enough for one of our benchmarking tests. So the last thing I want to talk about is in terms of using the Kubernetes approach is Jupyter notebooks. So at this point, what we are doing is basically in the container, we pick up the standard TensorFlow container. In this case, it was a little older one. You can use a newer one too. And what we did is actually install Jupyter using pip into my home directory in this case, in the example, but you could put it into any directory you want. And then I also created a cert file. You probably don't need this. You can run it without a cert because we're going to port forward over SSH anyway. So it doesn't, it should be okay to do it this way. But anyway, you could set up a cert if you want to. So once the Jupyter notebook is running, it's going to be on the default port of 888. So what I'm doing is using the kubectl port forward option to forward that port from the pod to the login node, right? And so I'm using 888 again, but if that port's taken, you can just use some other port. That should be okay. So you port forward it to the login node, and then I tunnel in from my client, which is my laptop, basically to forward that port from the login node to my client machine. So once that is there, you're effectively going to see the notebook on the 888 port on your client, which is your laptop, and which is what I did. And then open up the browser, and I can work with the notebook there. So it's a little tedious, but doable is what I would say. And what we are trying to do is we have on our other systems, we have a satellite service and that we use to kind of handle all these SSH aspects. And we think we can set that up on Voyager also. So once we do that, it'll be a lot easier to use this. But for now, if you need notebooks, this is the way you'll have to do it. So the last thing I want to kind of highlight some of these documents. So I'm going to open some of these and kind of show them, because it's pretty useful information. The first thing is the Habana model reference. This is a really nice place where basically they have examples and all the models that have been ported to both Gaudi and Gaudi 2, which is the newer processor. And they have the framework and all the information you need. So you can pick one of these and say, and they will have an example for that and a setup and everything. So it's actually very nice. So if you're using some of these standard models that they've already ported, you will have a pretty easy time porting your code over to Voyager. And they're constantly updating these and getting new models ported and so on. So, and I think if I remember right, they may have a roadmap link also somewhere. I'm trying to remember if it was here or it might be on their developer site, but they actually have more information on that. But so this is one great site. Then you should also look at their user guides for each of the frameworks. So for example, if you look at the TensorFlow one, you can basically see all the details you kind of need to do things, right? And they actually have a migration guide that makes it very simple, takes the standard example and highlights the changes that you need to make and so on. So very useful information to kind of get started if you're new to the Habana side of things. And the other thing that's important, and this is true for PyTorch also, is the operator list that is supported. So this is a little deeper dive into what you can and cannot do on the Gaudi. So this is the sort of thing we'll go into detail when we have the initial call with the group, right? Like we find out like what model they're using and if they have any specific operators that they need supported and so on. And they have the list of all the supported operators here. So you can take a look at this also. I mean, in advance of talking to us, or when we talk to you, the Habana experts will be on, and they'll probably look at your code and kind of figure out what's supported and what's not. Again, this is a ever evolving list, so you should take a look at that. And so similar thing for PyTorch. You can take a look at the supported operators and the user guide there. So you can see all the PyTorch operators and all the FP32, BF16, and so on. So you can kind of get a quick look at what supported and what you can use right away, basically. So that's one aspect of it. And then there are references on the API. So this is if you really want to go into the guts of things and start doing things, right? So like, for example, this is a reference on the HCCL, and there is a reference on the TPC also. So the API, it's a C API for the TPC. But for example, here you can see the supported collectives, so the all reduce, broadcast, reduce, scatter, and so on. So all pretty much built on kind of emulating the nickel layer that is that you're used to with GPUs. But there is like a C API to this, so if you really want to write your own thing, you can. So you can take a look at those. But as Amit suggested, this is probably not something that you would dive into in the first few months. I would say do the standard things first and see if you can make everything work through either TensorFlow or PyTorch, and go from there, because this can get involved and need a lot more support and longer term kind of goal. So that's kind of a summary of all the available resources, and so lots of details there. So I think at this point I will start summarizing the whole talk. So main thing is applications on Voyager are being run through Kubernetes. The main mechanism to run the applications is basically to use kubectl commands. In the future, we're going to have a GUI-based converge IO solution that might be more like easier for some users. I've seen it both ways. Like some people prefer the command line and kind of having to control everything, or you use something like Converge that lets you deploy solutions graphically. So that's coming down the pipe. One thing to note about Converge is that it will probably make the Jupyter Notebook setup a lot easier, because they have a application for that already. The software stack basically is made available with pre-built containers. You can take the container and add to it as you want. As I mentioned, the workflow, maybe the best workflow is to basically use the pre-built container, try out like the packages you want to install using, install them using pip and in your home directory or something like that. See if everything you need is in there and it works. Once it does, go back to the container, add all of the packages that you added. So then you have a working container for your workflow. And that'll be probably the best way to do it. When you're testing things, it might be easier to just, do pip install them. And as you saw, you can access the running pod and within the container environment interactively. So that's easy to kind of play around with things. And you can pull in any directories that are mounted on the host. So you can pull in the home directory, the Ceph based, and then there is a node local NVMe based storage that is basically scratch space that you can use. We have example YAML files on the system in CM shared apps, SDSC, and once we do an onboarding call with you, we'll give you. We usually walk users from a group through like all the mechanisms to run and so on. You've seen it already, but we can do an interactive walkthrough with people. But we have example YAML file for single card, multi-card, single node, and multi-node execution. All of that is possible. We in general, I think this is an evolving set of files because Habana is pretty aggressively adding to the models, improving the Synapse AI software continuously. And a lot of the testbed phase, I think it'll inform some of the changes and kind of performance improvements. So expect that you will be changing these containers relatively often, like I would say every 2 or 3 months. So what I'm trying to say is, if you are adding packages to a container, to the default container, just have those in like definition files or something that can be replicated easily, so that you can quickly take a new pre-built container and add to that and get a new container, because this is a dynamic target essentially. It's a little different from what we do on a typical HPC system, where it's like, oh yeah, software installed, that's it, like it's going to be there for 2 years. Like that doesn't happen here. Like, so it's going to be a little different. You're going to be evolving along. But the good news is, there's the reason for that is performance improvement. So, and more support for extra models and operators and so on. So that's continuous improvement and new features. So it's good. That way, it's really good. So I think at this point, I'll stop and see if there are any more questions and any general discussion we want to have.
Yeah, thanks, Mahi. Yeah, we're open for question. I want to stress the last bullet of Mahi, because you saw a lot of things maybe go by a little fast, but like Mahi said, last bullet is the most important. You don't have to memorize or remember or take notes of anything and everything he said. You got a general idea of how Kubernetes. We will provide you with a starting, YAML file where you will literally be able to change some things, few things, and get going. So this was more of information exchange than, you having to know how to exactly use, create a YAML file, and we will do one-on-one boarding. So that's why we want to have, few groups of users that we can work. Let them go, they explore, and then bring in another group of users and things like that. But yeah, if you have any question, please go ahead, either speak or write in the YAML file. And we are also recording it, and we will make it available. It will take a little bit of time because our events people, go through. I think they make it available through YouTube. It might take a few weeks. So then you can share it with your colleagues or any other collaborators, or anyone you think would be interested. We'll appreciate very much if you forward the YouTube when it's ready.